All right, so I'm going to finish up the video for 2.4, and we're going to look at what we call the composite function theorem. This is helpful if you have a composition of functions and you're doing a limit. So what this says is if you have a continuous function, f of x is continuous at L, and the limit of g of x, and g of x is this function that's inside of the function f of x, if that's equal to L, then what you can do is if you have the limit of f composed of g of x, you can do f of the limit of g of x equals f of L. Okay, so it's just as well to just demonstrate this on a few examples. These are pretty good examples of the kind of thing you'll do this for. These are two trigonometric functions. So let me show you what this thing is saying. So first of all, the g of x in this formula is the function that's inside of a bigger function. So 2x is a function, and it's inside of a bigger function, cosine of x. So what happens on this, really, if you think about this, is the way I've got this set up, if you were doing f composed of g of x, you would replace the x with 2x, and you would just get cosine of 2x. So what you do on this, according to this theorem, is you can do this like this, okay? The outside function is the cosine. So what you could do is when you're doing this limit, you could do the cosine of the limit of the inside function, 2x, as x approaches pi over 2. Okay, so that's what that theorem says. See, the outer function is f, that's the cosine. The inner function, you're doing the limit of the inner function 2x. Now, here's what you do. And you actually don't have to do the problem this way. I mean, you could just plug the pi over 2 in. There's benefit of doing the problem this way on certain functions. So if you just plug in here, you would have the cosine. And when you do the limit of 2x, see, 2x is a continuous function. It's linear, it's continuous everywhere. So all you got to do is just plug in the pi over 2. So you would have 2 times, and then you would have pi over 2, like that. Of course, what would happen? The 2's would cancel out, of course, so you'd be left with the cosine of pi. And the cosine of pi, okay, well, don't forget your unit circle, all right? You got pi over here, -1, 0, so what's the cosine? The cosine is always the x value, so therefore the answer to this problem would be -1, okay? So that's how this composite theorem works, okay? You probably won't use this all that much. It is useful in certain cases, though. Okay, so the next one kind of goes like this. The first thing I would do on this one is this 3 is a constant. You don't necessarily have to do this, but this would probably be the best starting approach, is you can pull constants multiplied by a function outside of a limit. So you would have 3 times the limit as x approaches pi over 4 of tangent of x minus pi over 4, like that. Okay, so I'm going to start like that, and really what we want to do is g of x is the function embedded inside of another function. So think of this as the inside function. Okay, so that inside function is going to be x minus pi over 4. Okay, that outside function is going to be the tangent of something. So that will be tangent of x. Now, see, what you got to understand is in this problem, f composed of g of x, well, what do? You plug g into the x's for f of x. So you would have tangent of x minus pi over 4. You might have to review the composition of functions you do in pre-calc or college algebra. So now that we got this set up, well, here's essentially what we do. I'm going to write this down like this. So first of all, we took out the constant of 3, which is a good starting point on the problem. You can always pull constants out of limits, and then that would go like that. Okay, and then according to this property, again, the outer function, you're going to evaluate the limit of the inside function first, then plug that into f. So this would go like this. We have 3 times, the outer function is a tangent, and inside of that, you're going to do the limit as x approaches pi over 4 of the inner function, which is x minus pi over 4. So see, that's what that is. That is basically telling you that you can do that then. Okay? So what do you do now? All right, well, first of all, this is a linear function. Technically, x minus pi over 4 is linear. So you just plug this in, work it out. Okay, so I'll write down what we have left here. So we have 3 times the tangent, and then we're going to have the limit. Or hold on, we don't need to do the limit. We just need to plug the number in. Okay, so if we plug in that pi over 4, we get pi over 4 minus pi over 4. So we're ultimately going to just do the tangent of 0. So we're going to have 3 tangent of 0. Okay, and again, on a unit circle, if you're at 0 radians, you're looking at the point 1, 0. Remember, the tangent is y over x. So y is 0, x is 1, so you do 0 over 1. Therefore, the tangent of 0 radians is equal to 0. So you end up with 3 times 0. Therefore, the answer to that problem is 0. And like any of these problems with limits, I mean, you can pretty easily graph these. I don't want to do this on every problem, but I think it's probably worth doing on some of these. So what I would do in this problem, just to check and see if you're getting this right, is just put in the function 3 tangent x minus pi over 4. Okay, like this. Okay, you want to make sure that you're in radian mode when you do this. So I got 3 tangent x minus pi over 4. Check that you're in radian. See, I'm glad I checked that. Okay, I got to get myself in radian mode. And you can make a window around this limit. It's up to you. What I'm going to do is just go, since this is pi over 4, I'm going to go like something like 0 to maybe pi over 2. Okay, it's up to you though, as long as pi over 4 is inside of between 0 and x max. You can scale by whatever you want to. Let's scale by pi over 4 on this. It's just kind of a personal decision. This is probably okay. Negative 10 to 10 is probably okay, so I'll graph it. And this is pi over 4 right here. I think you can pretty clearly see that limit is going to 0 on that then. So again, you could trace, if you trace at pi over 4, which is where the limit goes, and that's closing in on 0. The function's continuous there anyway, right? So you don't have an asymptote or anything there. Okay, so that's how you do that. I just want you to get comfortable with this composite function theorem. There's occasional times when it's useful to do this. Both of these problems I just did, you could just as easily plug in the pi over 2, get the answer. This one, you could just as easily do that. But I do want to get you comfortable with this idea. So going down here, I want to see if you can repeat what I just did. Identify f of x and g of x. Remember, g of x is the inner function that is plugged into the outer function f of x. Do that, identify the f and g of x, and then use the theorem to see if you can do this. Okay. Pause, and then come back and check and see if you did it like your teacher did it. Okay, so you can go ahead and check and see if you got the results I got. And this is one of these things that's kind of, you're kind of wondering, this makes it look more complicated. Yeah, it's just as easy on all these examples to just simply plug in the value that x is approaching. That's ultimately what we end up doing on this. This theorem becomes useful in proving other theorems later in the class. So it's just kind of important to get a feel for how this theorem works, because it's mostly used for proofs of other properties. Okay, so the idea with this is what I would want you to do, negative 10 on the first one, 1 over e on the second one. I don't want a decimal. And if you have e to the negative 1, that's okay. It's just preferred to go ahead and change that to a positive exponent. Then you have 0. So if you need to look over this, you can. The key thing on this is the g of x would be x minus pi over 4. F of x, it's up to you. You could have secant of x, or you could have negative 10 secant of x. So if you put negative 10 secant x there, you're not wrong. What I elected to do was to bring the constant negative 10 out. It's a good habit to develop. Then you would be doing the limit of the secant of x minus pi over 4 after you pull out the negative 10, and then the composite theorem, composite function theorem, you're going to do the secant of the limit of the inside function x minus pi over 4. When you do this limit, the x minus pi over 4 is a linear function. Plug in, you're going to get 0. So the value of that limit is 0. So you have negative 10 times secant of 0. Now again, you don't always want to have to go find a unit circle. You want to be able to create unit circles on the fly as they pop up. That's important for higher math too. So what happens is if you're at 0 radians, you're at the point 1, 0. And remember the secant's definition, you can think of it as the reciprocal of the cosine, or you can think of it as r over x. Unit circle r is 1, x is 1, therefore that's 1. Okay, then 1 times negative 10 is 10. So that's how I figured that out. I went ahead and put the graph in. And if you put the graph in, the way you have to put the graph in on this, by the way, is you have to go negative 10, 1 over cosine of x minus pi over 4. That's how you put a secant in your graphing calculator. So anyway, I made my graph go from 0 to pi over 2 here. And we're doing the limit as x goes to pi over 4. So if you put this in, you can tell as you're closing in on pi over 4, you can tell that y value is approaching negative 10. I think I had my scale set up so it went 5, 10, 15, 20, like that. So that makes it pretty clear that I have the right answer. The next one, the inside function, is actually the 2x minus 1. And then the outer function, the bigger function, is e to the x. So if you're doing the composition of functions, you're plugging the 2x minus 1 in for x. Okay, so this is how I went about doing it. I write it this way. It looks kind of weird, but this is the way you do it. You'd have e, and in the exponent, you would have the limit of 2x minus 1. Plug in the 0. That exponent is going to work out to be negative 1, so you get e to the negative 1. And here's the graph. I went ahead and graphed the original function on the calculator. You can pretty well tell on this as x approaches 0. Those two double arrows are showing left-hand limit. And this is 1 over e. What you'll find on your graphing calculator is you get like, I think, 0.36 or something like that. And then you can check and verify that 1 over e is the same as the decimal equivalent that your calculator is getting. And let's say the last one, I got 0. The inner function is x minus 1. Outer function is ln x. Or again, you could have 4 ln x. I just chose to bring the 4 out like I did here. So here's how you go through this then. Bring the 4 out, and then do ln of the limit of x minus 1. Plug in the 2. You're going to have ln of 1. ln of 1 is 0. Therefore, the answer is 0. And then here's a graph that shows what the graph of 4 ln x minus 1 looks like. Okay, and you can pretty well tell as x goes to 2, you're closing in on a function value of 0. Okay, so mostly that's arithmetic when you get right down to it. Okay, so I'll move to this last page, and we're going to talk about what the intermediate value theorem says on this. So let me just kind of read this, and let's see if we can make sense of what this says. So this says you have f is a continuous function. Sorry, I'm yawning. Okay, so we have f is a continuous function. It's a closed bounded interval, and that's real important. So that's why you have the brackets on that. That's what makes it a closed interval from just two specific points, A to B. Okay, and then if z is any real number between f of A and f of B, then there must be a number c in that interval such that f of c is equal to z. Now, as you start getting higher in math, you have to start reading textbooks more, and you got to start looking at definitions and making sense of them. Mathematics has the hallmark that you can define things extremely precisely. That's what's great about mathematics. So let's see if we can make sense of this. Actually, it's real simple. You have a continuous function. There's no breaks in the function anywhere, and you're just interested on the interval A to B. You have a closed interval on that. All right, so that's the first part of that. Okay, it says, let's assume that we have a real number z that is between f of A. F of A is just the y value given that A, and f of B. And f of B is just the y value of this second number. So you got f of a and then you got f of b. So it's saying if z is a y value between f of a and f of b, then you're guaranteed to find a number c that's in between a and b. So what it's saying is if you have a continuous function on a closed interval, if you choose a number z between f of a and f of b, then you're guaranteed to find a x value between a and b. That's how you would make sense of that in words then. That's the idea, okay? So I'll kind of run through, just going to do a little bit of work with this, not going to do too much with this. So the idea with this is we're going to look at if f of x is x to the second as the function. Again, we have a closed interval 1 to 4, and z is 5. We're going to see, is there a value c such that f of c is equal to z? So a good way to start this is we're going to go ahead and just do, let's just do a graph like this on this interval so we can visualize what's going on. So let's just go 1, 2, 3, 4. So we're interested on the closed interval 1 to 4. And if you graph this function, I mean, you don't have to use a calculator. I'm going to go ahead and do this, though, on this. Let's just kind of look at how this goes then. So I'm just going to put in y equals x squared. That's a parabola, quadratic function. Let's go zoom 6, get a standard window. And we're interested from 1 to 4. You definitely have a continuous function in there. So the idea would kind of go like this. All right, this is kind of what I want you to think about here. So let's just say that's 1, 4 to the second, 16. Okay, so let's say that's 16 like this. And I'm not drawing a super accurate graph, I'm just trying to give you kind of an idea here. That's kind of the key thing. So what you have is you can think of A as being 1, B as being 4. That's the endpoints of that interval. Then f of A is equal to 1. That's the y value. And then f of B is going to be equal to 16. Okay, so here's kind of what we have here then. Okay, it says z is 5. Okay, so here's the thing. Z, you have a z, and notice that 5 is in the middle of a and b, because after all, a and b are 4. So you have, whoa, did I do that? Oh, no. I know what I did. I'm sorry, I'm thinking wrong. Z is a function value. So the idea is the z has to be in the middle of f of b and f of a. Now that's what the intermediate value theorem says. F of a is 1, z is 5, f of b is 16. So this z is right there. So what this intermediate value theorem is saying this. Okay, we have a z in between these function values. We should be able to find an x that's between 1 and 4. You can tell visually that's going to happen. So the answer to that's yes. And then the question is, how do we find it? Well, it's simple to find it. You have f of x is equal to x squared. F of x is 5. So you'd have 5 equals x squared. Solve that equation. You take square root of both sides, and you would use the positive square root of 5. So that would be the x value that provides that value then, okay? So the value of x, and notice that 1 is less than square root of 5 is less than 4, because the square root of 5 is like 2 point something, okay? So that's the idea. So it's real logical what you can do on the intermediate value theorem. Okay, so notice if I do square root of 5, I get something between 1 and 4. And 1 and 4 was the initial interval that I gave you. Okay, so that's it. So again, if 5 is between 1 and 16, which it is, then you can find an x value for this function that's between 1 and 4. That's the meaning of that problem. Okay? Okay, so let's see. The next problem says, if f of x equals 1 over x minus 2 on the interval 0 to 4 and z is 0, is there a value c such that f of c equals z? So let's look at this. You have to pay attention to the definition, but let's go ahead and let's just construct a graph. We can use our calculator to help us with the graph here. So we're going to look at a closed interval. So we have to have a closed interval, so that's cool. So we have that. Now, the other thing I want to ask you is this. All right, this is kind of key in this problem. Where is this undefined? In other words, where do you have a vertical asymptote? Okay, you have a vertical asymptote at x equals 2. Good. Okay, so that is going to violate one of the conditions of this theorem. But let's go ahead and let's just graph this, okay? And then I'll kind of show you what happens on this. And I already know that the intermediate value theorem is going to fail, and here's why I know this. Look what it says. It says f must be continuous over this closed interval. You are not continuous because you're undefined at 2, which is between 0 and 4. Okay, so let's just go ahead and graph it. You'll see real clearly, I think, why the intermediate value theorem fails on this problem. Okay, so we got this. Let's just do kind of, let's just do the window 0 to 4. So we're only focusing on that part of the graph. And this will probably be good enough. All right, so here's the thing. And I'm going to slide a picture of this over here for a second, so we can kind of see this pretty clearly. Okay. All right, so here's kind of the idea. And just go ahead and sketch in kind of what this graph is saying on the calculator. So what you've got is you've got the way you would expect it to work around an asymptote. It's going like that. So here's what happens on this problem. So it says that z is 0. So there's your z value. Now here's what the problem is, okay? First of all, if you have this, if you have 0 and 4 as your open interval, a would be 0, b would be 4. F of a would be 1 over 0 minus 2, so that would be negative 1/2. So this function value right here is negative 1/2. Okay, the value of z is 0, so that's right there. And then the other thing is f of b, f of 4, would be equal to 1 over 4 minus 2, so that's 1/2. Okay, like that. So if you get way over here, then this function value right here is 1/2. So according to this theorem, it says that you can find a value of x in between 0 and 4 such that that x value is between, what it's saying is z is between the function values, and it is. The function values are negative 1.5, like that. If you look at the intermediate value theorem and what it says then there is a number c in the interval such that f of c is z. Now this is not true in this problem. If you look at this problem, f of 0, okay, or f of c equals 0, there's no x value that provides that y value of 0. This fails. And the reason this fails, and then the answer to this is no, the reason it fails is because the function is not continuous on that interval 0 to 4. Okay, that's why it fails. Now, you got to think about that a little bit. Okay, so not continuous on 0 to 4, so that means you cannot use the intermediate value theorem. I'm just going to say intermediate value theorem can't be used. Okay, again, that violates the first condition that you have to have a continuous function. So if your function's not continuous on your interval, don't even bother with it. Okay, I was trying to show you an example of where you can tell that doesn't work. Okay, so again, the value of z they gave you 0 is between f of a and f of b. It's clearly between negative 1.5. That's good. So according to this, it says there's a value c, which just means an x value. So it says you can find an x value that will have a y value of 0. No, you can't. You can't at all on this problem. Not on, and that's because it's discontinuous. So that's the idea. Okay? Think about that. When you look at mathematics at a higher level, you just got to read every little piece of a definition and follow every part of that definition. Okay, so let's look at the next one. So let's see. We have a closed interval -2 to 2. That's good. So let's go ahead and let's just draw ourselves a graph like that. Okay, and then we're going to graph this function 1 minus x squared. So let's go ahead and just do this on graphing calculator. Now this is a quadratic function, so its graph is going to be a parabola. All right, let's just do this from, just like we're asked to, -2 to 2. Come on, stop that. -2, set up the window, -2 to 2. Whoops. And scale by 1, and let's go like -10 to 10. Scaling the y like that. Okay, and then we'll do a graph just to get enough values. Okay, so what I'm going to do on this then is we're going to construct a graph like that, but let me show you kind of what we're going to be doing with this intermediate value theorem then. Okay, I want to slide that over at the side here. Just minimize that, okay, for a minute. Okay, so here's what we have. All right, A is -2. B is 2. So we're going to see if the intermediate value theorem holds on this. Question number 1 is this function continuous on this interval? Yeah, this function, if you look at the graphing calculator, the function's continuous. There's no breaks, no asymptotes. So are we continuous on the interval -2 to 2? Yes. Okay, so we're good there. All right, and then if you look at the intermediate value theorem, so you got to read the theorem and do exactly what it says. Okay, we're continuous, check. Closed bounded interval. We're just going -2 to 2. That's a closed interval. And now it says if z is between f of a and f of b. Let's pause there and let's do this then. Okay, so let's do this. Let's just do a couple of function values here. So we have f of -2 would be 1 minus -2 squared. So that's 1 minus 4, so that's -3. Okay, and then we're going to construct ourselves a graph on here. So I'm just going to put this function value right there. So that's what f of -2 is. All right. Okay, then let's do f of 2, which I think you'll get the same thing. So you got 1 minus 2 to the second. That's 1 minus 4, so that's -3. Okay, so you get the same thing there, all right? And the graph looks like this. Okay, you've end up getting, and you would end up like if you did f of 0, by the way, you would have 1 minus 0 squared, so you'd have 1. So let's just get ourselves a little sketch of this graph then. So the graph kind of does something like this. It's a quadratic function going like that. Okay, so we got that. We know it's a continuous function. Okay, yes. Okay, now the next thing is they're saying z equals 2. So here's the problem with this then. Okay, so if z, which is equal to 2, is between f of a and f of b, then we can find a number x that would have that value of 2. So first of all, if you look at this right here, that's where y is 2. There is not an x value in this interval that has 2. You can tell that by looking. The max is 1. So why does the intermediate value theorem fail? It fails because of this. This is not true. So z is not between -3 and -3. Okay, so the intermediate value theorem will fail. Okay, that's why. There's always, if all the conditions are met, then it will be a guarantee that you can find an x value on the interval that has this y value represented by z. Okay, so as I go over these problems, think about the conditions on this. I'm going to slide on this and zoom on this one more time. Okay, intermediate value theorem. When does it hold? When the function's continuous on a closed interval, okay, that's bounded, okay, no asymptotes or anything like that. And it's got to be nice and smooth, no holes, no asymptotes. Then if z is a y value, a real number between these two y values, then you will be able to find a y value represented by c such that f of c equals z. So just go back to the diagram again. Here's a continuous function. Z is between f of a and f of b. So if this is a continuous function on a bounded interval a to b, then you're absolutely guaranteed, as long as z is between f of a and f of b, then you're guaranteed to be able to find a c that's between a and b. Okay, that's what it means. Okay, so think about that. Okay, so that'll wrap us up then, and that'll wrap up this section. Kind of a long section, and this actually kind of gets us closer to the end of limits. In the next section, we'll look at the very precise technical definition of what a limit is. We haven't done that yet, so that's the next thing.